going to do a third optimization problem. This one says find two positive numbers, the sum of which is 100, and the square of one times twice the cube of the other is to be maximized. This you can't really get a diagram out of, but you can directly translate the words into equations. So our first part says find two positive numbers, the sum of which is 100. Stop right there, let's give their two numbers, let them be x and y, and make them added together to equal 100. Then it says the square of 1, so let's call this one x squared, times twice the cube of the other, times 2y cubed, is to be maximized. Okay? A lot of people have problems with what to put here. I'm just going to put m. Moral of the story is it could be anything. You can have p, you can have x, well, you can't have x. You can have p, you can have z, you can have omega, you can have a small, tiny miniature Eiffel Tower. It doesn't matter. This is the value that has to be maximized. It's just a variable. Just don't put x and y or you get confused. So what we need to do is have this m value in terms of either x or y. I'm going to make it in terms of y because if I change this so that it's x equals 100 minus y and plug that in here, I'm going to have 100 minus y squared times 2y cubed. And that's an easier way than if I had it in terms of x and had to deal with 100 minus x being cubed. Let's expand this. 100 minus y should give 10,000 minus 200y plus y squared, all times 2y cubed. So we should then have 20,000 minus 400y, so 20,000 y cubed minus 400 y to the 4 plus 2y to the 5. And this is m of y that you can now find the derivative of and set that equal to 0 to make sure we're maximizing this value. M prime of y is going to be 60,000 y squared minus 1,600 y cubed plus 10y to the 4. Once we have that, we can factor out 10y squared immediately. 10y squared, and we're going to have 6,000 minus 160y plus y squared. Now we can just factor these terms to find when this value equals 0. 10y squared, this factored, you have y minus 100 and y minus 60. Okay? So our possible values of y here are y equals 0, or 100, or 60. Now we want to find this when it's maximized. Okay? That's the key thing in this question. And if we plug y back into our x value here, and if it's 0, our x is going to be 100. But 100 times 0 is not going to maximize this equation. And if we have 100 in here, we're going to have x being 0, and once again 100 times 0 doesn't maximize. So we need to choose 60. These are two minimum values. X will be a maximum, or sorry, 60 will be a maximum such that x is 100 minus 60, and x equals 40. So our two values that maximize this equation are 40 and 60. That's a third example of an optimization problem.